Welcome back to another explainer. Today, we're jumping straight into a topic that is literally the backbone of probability, statistics, and even computer science. We're demystifying counting by mastering permutations and combinations. Now, if you're gearing up for highly competitive exams, like the IIT JEE, you already know that manually listing out possibilities is a fast track to running completely out of time. So my goal today is to equip you with the mathematical superpowers you need to conquer these counting techniques with absolute confidence. Let's get into it. Here's our roadmap for this explainer. We are going to build our toolkit piece by piece. We'll kick things off with the fundamental principle of counting, then introduce factorials as our building blocks. From there, we tackle permutations when order matters and combinations for simple selections. We'll compare the two side by side, and finally, wrap up with some quick tips and real-world applications. Section 1. Fundamental principle of counting. Okay, let's dive into the absolute foundation of all counting techniques.
Picture this. You're setting up a new online account, and the system asks you to create a password. It needs exactly 2 letters followed by exactly 3 digits. Now think about trying to write out every single possible combination by hand. You'd start with AA000, then AA001. You would literally be sitting there for years. This massive, seemingly impossible scenario instantly shows us why manual counting just isn't going to cut it when the stakes get higher. The actual answer? It's 676,000. And we get there in seconds using the multiplication principle. This principle tells us that if independent events are happening together, we simply multiply their individual possibilities. For that password, we have 26 options for the first letter, 26 for the second, 10 for the first digit, 10 for the second, and 10 for the third. Multiply them all together. 26 times 26 times 10 times 10 times 10. Boom, 676,000. It's the exact same logic as having, say, 3 shirts and 4 trousers. You just multiply 3 by 4, and you instantly know you have 12 different output combinations. Section 2, Factorials, the building blocks. Now that we've got multiplying independent events down, let's introduce the core mathematical tool we need to build much more complex counting structures. This tool is the factorial. In math, it's represented by an exclamation point. And a factorial is simply the product of all positive integers up to a given number. So if you see 5 factorial, it just means 5 times 4 times 3 times 2 times 1, which equals 120. 6 factorial, that jumps to 720. As you can see, it scales up incredibly fast. But here is an absolutely crucial point. Pay very close attention to these easily forgotten rules. 1 factorial equals 1, and 0 factorial also equals 1. Seriously, lock that into your memory right now. It's going to save you when the formulas get tricky later on. Section 3. Permutations, when order matters. All right, with factorials securely in our toolkit, we are ready to tackle our first major formula structure. And as we do, I want you to repeat a critical mantra in your head. Does order matter? A permutation is an arrangement of objects where the order absolutely matters. The formula is P of n, r, which equals n factorial divided by n minus r factorial. Let's break those variables down. It's actually pretty simple. N is the total number of distinct objects you're starting with, and R is the number of objects you are actually selecting and arranging. For example, say you want to arrange 3 letters from a pool of 4 distinct letters, A, B, C, and D. Your N is 4 and your R is 3. Plug that in, 4 factorial divided by 4 minus 3 factorial. That simplifies to 24 divided by 1, which gives us exactly 24 distinct ordered arrangements. Now, what's really cool is how this formula beautifully simplifies in a couple of special cases. If you're arranging all of the objects, like, say, arranging 5 students in a linear row, your R equals your N. The formula collapses down to just n factorial. So 5 students in a row, that's 5 factorial, or 120 ways. But watch out for circles. If you arrange objects in a circle, like placing 6 students around a round table, the starting point shifts. For this, we use the circular permutation shortcut, n minus 1 factorial. So for our 6 students, it becomes 5 factorial, bringing us right back to 120 ways. Section 4. Combinations, simple selections. Let's move on and see how this builds into our second major structure, where our golden mantra fundamentally changes. We're now looking at combinations. A combination is a selection of objects where the order does not matter at all. We are simply grouping things together. The formula, C of nr, looks a lot like our permutation formula, but with one crucial addition in the denominator. We also divide by r factorial. Why? Because we need to strip away all those duplicate arrangements. For instance, if you just want to choose a group of 3 students from a total of 5, the order you pick them in doesn't matter. It's 5 factorial divided by the product of 3 factorial and 2 factorial. Work that out, and you get exactly 10 ways to form that specific group.
To make you even faster, let's walk through some incredible time-saving properties for combinations. Choosing 0 items or choosing all n items both yield exactly 1 way. Choosing 1 item from n yields n ways. But here is a massive, real game-changer shortcut. C of n, r is mathematically identical to C of n minus r. This means if you are calculating 8 choose 2, it gives you the exact same result as 8 choose 6. Both give you 28. Realizing that choosing who goes on the team is identically the same as choosing who gets left behind will save you precious minutes on a timed exam.
Section 5. Permutation versus combination. All right, we've reached the climax of our explainer. If there's one place where students consistently lose points, it is confusing these two concepts. Let's clear it up once and for all. And this brilliantly illustrates the ultimate aha moment. There is a fundamental conceptual separation here. Think about permutations as a strict arrangement. Order matters. ABC is fundamentally different from BAC. Think of it like the combination to a safe. Ironically, a combination lock should really be called a permutation lock. On the flip side, a combination is purely a selection. Order does not matter. The group ABC is the exact same group as BAC. Think of tossing fruits into a blender. The order you throw the strawberries and bananas in doesn't change the final smoothie.
Because these two concepts are so closely related, the math beautifully ties them together. The number of permutations is quite literally just the number of combinations multiplied by r factorial. In plain English, first you use a combination to select your simple group, and then you multiply by r factorial to find all the different ways you can arrange that specific group. Every single simple selection can be independently arranged in r factorial ways. It's like a giant, elegant puzzle coming together.
Section 6. Quick tips and applications. All right, let's shift into a high-energy, rapid-fire pace to lock all this theory into reality. Let's rapidly fire through some examples to prove how these formulas decode everyday problems. Forming a committee of 4 from 10 students, order doesn't matter, it's a combination. 10 choose 4 is 210. Arranging 5 distinct books on a shelf, order matters, and all objects are used. It's 5 factorial, which is 120 ways. Selecting a team of 2 from 8 players, just selecting, no arranging, so it's 8 choose 2, which is 28. Creating a specific 3-digit number from 4 available digits without repeating, order absolutely matters for numbers, so it's a permutation. P of 4, 3 equals 24.
If you're walking into the JEE, or really any high-pressure exam, you need a rapid mental checklist. You need to know exactly which mental model to trigger. Always ask the question, does order matter? Yes? Boom, permutation. No? Combination. Are you arranging distinct objects in a straight line? Use n factorial. Are they sitting in a circle? Immediately drop to n minus 1 factorial. Following this checklist ensures you don't accidentally do the wrong math perfectly right.
So the crucial takeaway all boils down to this. Consider this your ultimate, structured cheat sheet mapping the core concept directly to the formula. You've got factorials, permutations, combinations, circular arrangements, and that master relation tying P and C together. I highly encourage you to lock this summary into your memory. It literally represents the culmination of the fundamental principle of counting.
You now have the exact toolkit to bypass tedious manual counting and jump straight to the answer. You understand arrangements, you understand selections, and most importantly, you know how to tell them apart. Now that you hold this mathematical superpower to count the impossible, look around your world. What complex, real-life scenario are you going to decode next? Keep practicing, keep questioning, and keep learning. Catch you in the next explainer.